I'm Albert Feng. My own work actually is focused on neurobiology of hearing. The focus has been trying to gain an understanding of the neural basis of sound pattern recognition and sound localization. I've been involved in translational research with the development of intelligent hearing aids and currently with the development of high-resolution biomolecular cochlear implants. With hearing aids, the typical complaint is that I can hear you, but I don't understand you. So the problem is because most hearing aids are designed around solving the inability to hear at high frequencies due to the aging effect or due to explosive sound experience. And the device is basically an amplifier trying to amplify the sound that they cannot hear, but not taking into account of really what the ears have to provide the brain in terms of how the brain can interpret what the sound is. So namely, the device is not designed around solving the perceptual problem. Basically, we thought this is silly. We have advanced electronic system, and why is it that we cannot design something better that utilize some of the basic principles in the biological systems? After all animals have to solve this problem to hear in real-world environments, and frogs in particular, the animal model that I'm looking at, been studying for many years, that they can solve this problem even though they communicate in a very dense chorus, very noisy environment, much like a cocktail party. The director of the Beckman Institute at the time really thought this was a cool idea, namely transferring knowledge from basic neurobiology to solving a technical problem. And with that, then we began to try to incorporate the intelligence of the biological systems. After all, it has been evolved millions of years, and it really has been successful in solving such practical problems. Finding out how many sound sources are there, where they are, and then focusing on one of the sounds in nature and to extract that particular sound and ignoring all the other sounds in the ambience. The algorithm was developed actually rather quickly, but the implementation in developing into a real device actually took some more time, because after all, you really have to have very fast computers that can process the information in parallel, what we call massively parallel computation, and that's not what a computer is good at. The computer is good at doing serial processing. And so it took a while, 2 years or so, to develop a real-time device that performs well in a real-world environment, whereby it can actually extract a particular signal amidst a large number of interfering sounds and elevate that signal such that it can not only be heard, but it can be understood. We basically concluded the project several years ago and licensed our technologies to a hearing aid company. Thereafter, we started to think about, okay, now if we have to solve this major problem for people who are hearing impaired but not deaf, what would be the next problem? Once you're deaf, you really have to depend on the use of a cochlear implant to restore hearing and to understand speech. Currently, the limitation of the cochlear implant is that only a subset of the available electrodes are usable to restore hearing. And as such, its performance is somewhat limited. The ability to understand speech is limited to only clean speech, but not in most everyday environments. And its ability to perceive music is limited. What we try to do is to develop high-performance cochlear implants by use of molecular biology. And Therefore, we call this biomolecular cochlear implants. And we hope to increase the number of channels that are usable in the cochlear implant by doing some genetic tweaking, bringing the neurons closer to the electrodes to allow the patient to hear and understand speech. In the real-world environment, when there are other sound sources in the ambience, as well as enjoying music.
That's beautiful.
After 10 practices.